Okay, so let's try to understand scalars and vectors. Scalars and vectors, the C4 mathematics. I'll try to explain from the very beginning the scalars and vectors. So first look into scalars. Scalar. Okay, what is a scalar? The scalar is a very simple thing. Actually, we already know what a scalar is. A scalar is just a value. Just anything has a value, we would say it's a scalar. For an example, we can say 5. All the numbers are scalars. That's the reason we would say it's a number scale or a Wayne scale. Because why? There's a value. There are values. So it's a scalar. A scalar is just anything has a size. Any quantity which has a size is a scalar. Scalar, so we can say, simply speaking, scalar is a value, is a quantity with a value. Quantity with a value. With a value. This value, in terms of, in this context, there are few words for the value, for this value. I mean, just a value. We would say value, that is just an English word, that's true. And also we can use a word like modulus. Modulus. Or sometimes you say modulus. And also magnitude. I'll write here, but actually write here. Magnitude. Magnitude. So anything has a magnitude only, just a magnitude, we would say it's a scalar. This is pretty simple. So there are plenty of scalars. It's all the numbers, like we said. All the numbers, anything can be depicted as a number, is a scalar. For example, money is a scalar because why? It has a value. So there's nothing really special about it because we know about scalars already. Probably we didn't know the name, but now we know it's a scalar. Right, for example, I'm going to write some examples for scalars. All the numbers. All the numbers are scalars. There are special scalars in the context of physics and mechanics. For an example, things like length is a scalar. For an example, we would say it's 25 kilometers. That's a length, or 5 centimeters. So these are physical quantities you can measure physically, so we would say they're scalars. Examples would be, given some certain examples which appear in mathematics, especially in mechanics and physics. These are like length. Length is a scalar. Mass is a scalar. For example, we would say 5 kilos, 10 kilos. This length is measured by centimeters, meters, kilometers, nanometers, whatever you like. The mass is measured by, as we know, kilograms, grams, tons, so forth, or milligrams, whatever you like. There are some other things like energy. Energy, also a scalar, measured by joules. The whole idea here is saying a scalar is something which has a size, is a size. So that's a scalar. So a scalar has a size, and also it has some sort of a unit. There are some other ones as well, like for an example, speed is also a scalar. In physics, current is a scalar too. Pressure is a scalar. However, we are not really going into all these details because this is all about mathematics, pure mathematics. So we are trying to limit to a general idea. Scalar, that's all about scalars. Okay, so keep in your mind, scalar is a quantity, or you can even say physical quantity, if you like. Physical quantity. Actually, that word could be more appropriate. Physical quantity is a physical quantity. Physical. Physical quantity with a value. It has only a value, actually, with a value. Yeah, a value. It has nothing else incorporated with it. It has a value. A scalar is something has a value, or you can say modulus or a magnitude. Okay, so let's move forward then into vectors. So vectors are are the real topic, the real highlight of the topic. So vectors quite different from scalars. So let's look into vectors. Now vectors, on the other hand, unlike scalars, there are two properties for a vector. Any vector, there are two properties. Number one, a vector has something interesting, a direction. Vector has a direction. And also size, if not a magnitude, like in a scalar. So vector has direction and magnitude, if not a value to that. Magnitude. And also we can depict or illustrate a vector. So when illustrating a vector, we can easily illustrate a vector as an arrow. You can illustrate a vector as an arrow, like that. This is a vector. Why do we say a vector can be represented as an arrow? The reason is this. If you take an arrow has a size or a magnitude. And also, an arrow has a direction. That's given by the direction. So, an arrow actually satisfies these both properties. So, we would say, simply speaking, a vector is an arrow. So, any physical quantity can be depicted as an arrow, we would say is a vector. So, I think that's a good way of understanding vectors. The simple idea of a vector. Vector is an arrow. A vector quantity is a physical quantity. That can be depicted, if not illustrated. I will write depicted as an arrow. That's the vector. So try to recall if you know any quantities that has a direction and a magnitude both. Maybe you have learned in GCSEs or in physics, or if you've done some mechanics. There are many examples for vectors. Vectors are pretty important, very important. So let's discuss a bit more about vectors. Now, as we mentioned before, a vector is an arrow. Is an arrow. Simply speaking, is an arrow. Is an arrow. So this is a vector. Has a direction. Has a direction. This is the direction of a vector. And it has size. And a size. The length of the arrow gives the size of it, or the magnitude of it. That's give the direction of it. Now let's look into some examples of vectors. Examples of vectors. There's a very famous example that is called force. Force is a vector. Force. Why force is a vector? The reason is force means push or a pull. Force means push or a pull. As you know in physics or mechanics, force, the definition of a force is push or a pull. So as we know, when you're pushing or pulling something, there's a direction incorporated with it. The higher the pull, it'll come towards you at a greater speed, if it's going to move at all. So we can clearly see there's a size of it and also direction incorporated with it. So force is one of those vectors. There are some other too. Force. We have other things like velocity. Velocity means speed with a direction. Velocity means speed with a certain direction. On the other hand, force means push or pull. The reason I'm writing these things, then you can clearly see there's a direction incorporated with it and also a size. For an example, we would say force has 25 newtons. So we can depict it. So for an example, we can say force equals 25 newtons due east. So we can depict it like this. That's the east. That's the east. The 25 is a size. So this 25 should be incorporated with the size of the arrow. There's a size here that should be incorporated with the direction, with the size, 25. So the length of this one, if you want, can be 25 newtons, 25. And the direction is given by that direction. In a similar fashion, we can say velocity is, let's say, 10 meters per second due northeast. Let's say that's the case. Now, how do we depict this one? We can depict that easily. Let me explain to you here. Given velocity is 10 meters per second due northeast. And we know that is north, basically that's northeast, isn't it? Given that is east. That's north. That's northeast. Northeast means in this context it's like 45 degrees from north. So that's the northeast direction. So we can say, we can draw it like this. There you go. That's a vector. That's a vector for the velocity 10 meters per second. Now this 10 is a scalar, isn't it? 10 is a size. This size is related to the length of the vector. And also the direction is incorporated with the arrowhead. Okay. So I think it's clear, to depict something with a direction, we require an arrow. It's pretty simple and I think it's pretty straightforward and clear. So let's see how to move forward with this idea. Right. We always take the stance of this. A vector is an arrow. That's our stance. Right. Now let's look into vector algebra. If not vector addition and subtraction. Now before we go into vector addition, Now, you might be thinking, what do you mean by vector addition? If you look into scalars, we can add scalars. For example, 5 plus 3, we would say 8. 10 minus 3, we would say 7. Those are scalars we are adding and subtracting. Similarly, we can actually multiply as well. In a similar fashion, vectors also can be added, subtracted, and multiplied. But however, the rules of addition and subtraction or multiplication, the rules are different. Because why? The main reason, vectors has a direction. So whereas scalars don't have direction. So we had to follow certain different set of rules. So let's see what those rules are. However, before we go into that direction, we had to look into some other facets of vectors. Let's see what those things are. The nature of vectors. The nature of vectors. That's basically the basic nature of vectors. We are investigating here the very basic nature of vectors. So let's say we have a vector or an arrow like this. Like we mentioned before, the size of the physical quantity, that vector given by that, the length of it, and the direction is given by the direction of the arrowhead. Let me draw it again. Something better. Now, we can easily, there are a few things we can do. The vectors can be translated. Vectors can be translated. Vectors can be translated. Let me explain to you what this means. Vectors can be translated. Translated. A translation, it's like in C1 or C2 pure maths or core maths. We have learned translating graphs. You can move a graph like that, horizontally or vertically. Basically, what we are saying, we can move a vector across, or we can move a vector upwards, or we can do both. However, we cannot rotate a vector. I'll explain to you in a minute bit more with examples. Vectors can be translated. So, for an example, let's say an example. Let's say there's a vector here. This vector can be moved like that, parallelly. See? Now that's being translated there. That's also vector. Let's say this is a vector A, given by A. Vector A. That's also vector A. Exactly same. There's no harm done. A vector being translated. In a similar fashion, you can translate a vector just moving or vertically upwards. For example, like this. Let's say we have a vector like that. This can be translated like this. We can move upwards like this. See? Let's say that's a vector B. That's also vector B. Or we can do a bit of both. Like this. Let's say we have a vector like that. I can first translate the vector across like this. And now I can translate upwards. They're all the same thing. They all are the same thing. See, it's going to move now like this. So that's the original vector, vector A. We translate it, still vector A, there's no changes there. Translate again, still vector A. So by translating, the vectors don't change. As long as we are keeping the length and the direction exactly the same. We can translate as many times as we want. However, we can't rotate a vector. We can't rotate it like this. We cannot. If we do that, we are violating the vector. You will see those examples a bit later on when you're dealing with these things more. So we have established one rule. It's number one. Now let me write here. Vectors can be translated. It's allowed. Translated horizontally or vertically, or both. There's another one. We can do. Vectors can be enlarged by enlarging factor. Vectors can be enlarged. However, that's going to violate the size of the vector, but the direction remains the same. You will see in a minute how that is. Vectors can be enlarged by a scale factor. Vectors can be enlarged by a scale factor. Let's see what this means. Let's say we have a vector given by this. It's called vector B. I can enlarge this vector by elongating it in the same direction. For an example, I can draw this vector like this, twice the size. Twice the size. Now this is given as 2b. See? It's 2b, however, it has the same direction. Enlarged by a scale factor. The scale factor is 2 here. In this case, the scale factor is 2. The scale factor can be negative as well. Actually, I'll explain to you what happens then in a minute. So another example here, you can write. For example, let's say we have a vector like that, vector given by C. I can enlarge this one by a scale factor of 3. So it's going to become 3 times 3c. 3 times c, 3c. I can enlarge this one by 0.5. It's going to become half. They all are, however, parallel to each other. Or I can enlarge this one by 1.5. It's maybe like that. 1.5c. And you can see when I'm writing vectors, there's a dash here bottom. That's how to depict vectors, to distinguish between scalars and vectors. When you're writing just a scalar, we just write c, like a constant. But here, we write like a small dash to say vectors. Same here, under any letter, you write like that. Textbooks, however, they depict vectors as in a bold letter, but here I can't. This is not a textbook, so I'm just writing a small dash line. Okay. So that's a scale factor. I hope that's understandable. Right, now let's move forward with the scale factor a bit more. Let's say, another case, scale factor is given by -1. Scale factor is -1. Scale factor can be negative. Let's say we have a vector like this. Okay, let's say the vector is given by z, and the scale factor is given by -1. -1. So what happens here? This z become -z. However, in vectors, if this is z, the -z would be exactly opposite. They are still parallel, however, exactly opposite. So the -z would be look like this. Oops. Like this. That's -z. -z. C is minus. So it's appear to be, it's like a sort of a rotation, however, 360 degrees, 180 degrees in a sense. You can think like that. -z. So when the scale factor is negative, what happens is just change the direction of it. So minus refers to the opposite direction of vector. What we are saying here, furthermore, if we imply this one in other cases, we are saying here is this. Let's say that's vector A. Vector -a would be this. -a. So this vector B, vector -b would be exactly opposite. Minus. So scale factor can be negative. Scale factor can be -2, 3, 4, whatever value you like. So in that case, for an example, when the scale factor is like -2, let's say this scale factor is -2, then that's sort of reverse still, however size would be twice elongated, like this. So it will be -2z. Because the scale factor is -2. So minus refers to reversing, 2 refers to doubling. Okay. So in other words, if this refers to 25 newtons due northeast, this refers to 25 newtons due southwest. 25 newtons goes to the same size. Let's say that is 25 newtons. 25 newtons due northeast. This will be 25 newtons due southwest. Is an example. It's not required, but I'm just giving an example. Or we can say if this is 10 meters per second due north, that will be 10 meters per second due south. In a similar fashion, if this is 10 newtons due northeast, this will be 20 newtons due southwest, because it stands by 220 newtons due southeast. Example, 10 newtons due northeast. This will be 20 newtons due southwest. This knowledge of manipulating vectors are very essential to move forward systematically. So please try to understand what's really going on. Even though it appears to be very simple, maybe it is not simple as we think, because more we think, we learn about more things about vectors. Then it's become really simple, then with understanding. Okay. Cool. So in the next lesson, I'll explain to you how to add and subtract vectors. So you can watch the next clip, then you will learn how to subtract and add vectors and furthermore stuff.